So let us start the lecture. It's Banach contraction principle. Okay. Banach contraction principle. So first we define contraction mapping. Definition. Let X D be a metric space and T from X to X is a mapping. So we say that this T is contraction. We say that T is a contraction mapping. T is a contraction mapping if I can find some positive number less than 1, if there exists, or it's obviously a positive number, positive real number, okay, greater than 0. If there exists 0 less than or less than 1, such that distance between the images is lesser equal to r times distance between x and y. That's actually distance decreases between the points, because for if suppose distance between x and y is, say suppose r is equal to 0.5, suppose r is less than 1, and distance between x and y is say 2, then what will be r times 2? It will be 1. So that means the distance between the images is less or equal to 1. So distance it gets contracted, okay, if r is a positive number and less than 1. So this is called a contraction mapping. So we say T is a contraction mapping if we can find a positive number r with this property. This holds for each x, y, and x. It's a global property, okay? It's not local. It's true for each x, y. So that's here is an exercise for you. It's straightforward. Show that every contraction is continuous. Show that every contraction is continuous. So this is straightforward. Now we have it. Now we define fixed point. Okay. Define fixed point. So fixed point it's defined for a general set. We define it for a metric space. So let X be a metric space. Let X be a metric space, and T from X to X is a mapping. Is a okay. A point X not in X. A point X not in X, a point X not in X, a point X not in X is called a fixed point of T, is called a fixed point of T if T of X naught is same as X naught. Okay. So there are some examples. Let's take this example. Say let's define T on closed interval 0, 1 to closed interval 0 1. Let's define it by define t by define t of x equal to x square. So clearly 0 and 1 they are the fixed point. Clearly 0 and 1 they are both fixed points, because t of 0 is 0, t of 1 is 1, or fixed points, or fixed points of t. They are fixed points of t. So here t is not contraction mapping, but it has fixed points. So 0 and 1 they are the fixed points of t. We have another mapping. So if I define t by t of x equals to say x by 2, then 0 is the only fixed point. Then 0 is the only fixed point. Here t is the contraction. You can see this. We have t of x minus t of y. It's equal to 1 half x minus y half. That's equal to 1 by 2 times mod of x minus y. So this is our positive, which lies between 0 and 1. It's a contraction mapping. So it is only one fixed point here. So you can define like this: t of x equals to say I want a self mapping actually. So x minus 1 by 2, it maps 0 onto minus 1 by 2. That's a problem. Okay, so it will not work. You can take 1 by 3x as well. So this has a unique fixed point. This one. Okay. So let's now state this is also a contraction mapping. So let's now state this Banach contraction principle. Okay, theorem. This is Banach contraction principle. If T is a contraction mapping defined on a complete metric space, so let's start with a complete metric space. Let X D be a complete metric space, and this T is a contraction mapping, X to X. This be a contraction mapping, okay. Then this T has a unique fixed point, has a unique fixed point. जैसे अपने इन एग्जाम्पल्स में देखा टी एफ एक्स को 1/3, इसका भी यूनिक फिक्स्ड पॉइंट है 0, और इससे पहले जो एग्जाम्पल आपने दी it is also a unique fixed point, and here the space is complete again, 0 1 0 1. But in the previous example, let's see this t of x to x square. This is not a contraction mapping, and it is two fixed points. You can see 0 and 1. So if the space is complete and the mapping, this self mapping means the space to itself, x to x. If this self mapping is also contraction, then it has a unique fixed point. That's this theorem actually. So if it's a complete metric space and T is a contraction mapping, then T has a unique fixed point. So this is very important theorem, and the proof is very simple, but it has a number of applications in in the existence of a certain differential equations. Okay, existence of solution, like Picard's theorem. Picard's theorem इसकी applications है. So we so whenever you see a complete metric space, so it's clear that you must actually you must construct some Cauchy sequence, then you have to apply the convergence. So how do we construct that Cauchy sequence here? We begin with a point, so any arbitrary point in our space X, and we apply T repeatedly on that. Say T of find, then T, then again we apply T, then again we apply T, and we get a sequence of points, and we'll see that that sequence is a Cauchy sequence. Okay, so let's fix any point. So let X not be any arbitrary but a fixed point. Let X not be an arbitrary point in X. Okay, now we define the following sequence. Define the following. So this x naught is obviously the first term of this sequence. So let's define next term, which is x1. That's equal to t of x naught. Then you define one more term, that's equal to t square of x naught. Actually you are applying twice t on x naught, and first is it's t of x naught x1. तो जो आपको पॉइंट मिल रहा है by applying t on x naught x1, you apply t on that. Actually that's the next point. Now what will be x3? It's you are applying now t on x2, which is actually t cube on x naught. Okay, that's that you can easily verify, and so on and so forth. You will see, you will define xn, that's equal to t n of x naught, and that's actually the t of the n minus 1th point. Okay, like this. This is for all n greater or equal to 1. So we show that this xn is a Cauchy sequence. So we show that xn, n runs from 1 to infinity, is a Cauchy sequence. So in this direction, what we do first, we first verify that we first okay. So let's since t is contraction, let's apply the definition of contraction here. Since t is contraction, since t is contraction, so therefore there exists some r which lies between 0 and 1, such that distance between dx dy is less or equal to r times distance between x and y. Let's name it 1. Okay, by repeatedly applying 1, we get the following distance between t, say let's see this say p. Okay, t power p. So we are applying tp times an x. Okay, t power p y. We'll see that this is less or equal to r power p distance between x and y. So this is very simple. This one. This one is very simple. If you want to verify it, let's see this distance between t power p of x, t power p of y. So you are applying tp times here. This is equal to distance between t of t power p minus 1 of x, okay, t of t power p minus 1 of y, okay. Now since this t is contraction, so you can apply 1. It's less or equal to r times distance between the points. So points are here, these t power p minus 1x, t power p minus 1y. It's t power p minus 1x, t power p minus 1y. Now you see this is d times, you can write this as t times t power p minus 2x, okay, t of t power p minus 2 y. Again you apply the contraction property, so this is t of the point t power p minus 2x, t of the point where points t power p minus 2y. So it's less or equal to r, and r is already there here one, so it will be r square distance between t power p minus 2x, t power p minus 2. Continuing, you will finally see it will be less or equal to r power p distance between x and y. So this is okay. This one distance between t power px, t power py is less or equal to r power p times distance between x and y. This is true for all p greater or equal to 1. It's a positive integer, okay. So name it here 2. One more thing that you can do is again we have again this distance between, say again for n greater than 1, we have distance between xn minus 1 and xn, okay. This distance, let's see this distance between the two consecutive points of this sequence xn, okay. Okay. So I want here, I want d of x naught x1 here. This is equal to what? Distance between, what's xn minus 1? It's actually t n minus 1 of x naught, and this is t n of x naught, okay. First point is x naught, then the second point x1 is t of x naught, and the third point x2 is t square x naught, then the fourth is x3 which is t cube x naught, okay. So this is n minus, this is the nth point, actually it's t n minus 1 of x naught, and this n plus 1 entry point of the sequence, that's t power n of x naught. This is equal to, so I want to apply this here, this previous one, this 2. So for this I want the power same, actually p, okay. So this is distance between t n minus 1 x naught. The points may be different, but power must be same. It's, I will write it as t n minus 1 of t x naught, okay. This thing. So here the point is x naught, and here the point is t of x naught. Now the power is same, you can see. So you can apply this. This is less or equal to r power n minus 1 distance between what? It's now x naught and t of x naught, and that's equal to r power n minus 1 distance between x naught and x1. So note this one. This is equation number 3. This inequality 3 you can say. So distance between xn minus 1, xn is lesser equal to r power n minus 1 times distance between x naught, x1. Okay. So now you want to prove this Sweeken is the Cauchy Sweeken. That means you want to prove the distance between xn and xm, that distance approaching to 0 as n and m approaches to infinity. So let's choose m and n. Let m be, let's choose this m, it's less than n. I need two integers with m less than n. Then we have distance between xm and xn, and note that this m is less than n, so n minus m is a positive integer, n minus m. Now this one, it's equal to distance between t m of x naught, okay, and this was t power n of x naught. I want to apply second here, so for this I must have the same powers, but I know this m, it's less than n, okay, so I can write this as t power n as t power n minus m, because n minus m was positive, so positive power is defined here. T power m x naught, I write here t power m and then t power n minus m x naught. N minus m is positive, okay? So this is now by 2, this is less or equal to r power m times distance between this x naught and t power n minus m x naught. Okay. Now I will write it as r power n, distance between x naught, and this one is xn minus m, okay, xn minus m. Now let's apply the triangle inequality. Let's insert the points, say x1, x2 up to xn minus m minus 1. So you can see this is less or equal to, here it's by 2 here, okay. Now this is less or equal to this not 2, here it's by 2. Now this is less or equal to r power m. By triangle inequality you can write this as distance between x naught and x1 plus distance between x1 and x2 plus so on and so forth up to distance between x n minus m minus 1 and x n minus m. Okay, so r power is ये ठीक है, this one triangle inequality को मैंने अप्लाई किया है. So now this distance between x1 and x2, you can see this one x0 x1 as its CIC रहेगा. But what is the distance between, आपने ये निकाला ना, distance between xn minus 1 xn. So here n is 2, you can see. So distance between x1 x2, let's look at this page. Distance between x1 x2, okay. If n minus 1 is 1 and this n is 2, then so what's the distance between xn minus 1 and xn? So it's less or equal to r power 1 times distance between x0 x1 by 3, okay. So this is next page. Now this is less or equal to r power m times distance between x0 x1 x naught x1, this plus this r times distance between x naught x1 plus, you can see next term which that is distance between x2 x3, which is r square, distance between x naught x1 plus the last term is its last term, that's x power n minus m minus 1 x power, so it will be r power n minus m minus 1 times distance between x naught x1. So that's equal to distance between x naught x1, it's the common term here, this is here r power m times here it will be 1 plus r square plus r power n minus m minus 1. Okay, so that's less than distance between x naught x1 times r power m times 1 plus r square, it's infinite series. Okay. In fact, it is strictly less than. Okay, now this is equal to distance between x naught x1 r power m times, what is this? This is the first term divided by 1 minus the common ratio, that's r here. So that's it. Okay, so this means so therefore we have distance between x and xm is less than what? It's r power m divided by 1 minus r times distance between x naught x1. So r is less than 1, so if m is approaches to infinity, r power m will approach to 0. So but whenever m approaches to infinity, n will also approach to infinity, because n is greater than m. Okay, so this means the distance between, so which approach to 0 as n approach to infinity. Okay, now it's not n here, it's m here. Okay, because the power is m here, as because 0 less than or less than 1. So this implies distance between x and xm is approach to 0 as what? As m approach to infinity. Now this n is greater than m, so that means both n and m will approach to infinity. That means this means distance between x and xm approach to 0 as nm approach to infinity. So which implies this xn runs from 1 to infinity is a Cauchy sequence. This is a Cauchy sequence. Okay, this is a Cauchy sequence. Now since x is complete, since x is a complete metric space, since x is a complete metric space, so therefore there exists x in x such that x and converge to x. But then since t is continuous, this means t of x and approach to t of x as t is continuous, because every contraction is continuous, as t is continuous. Okay, as t is a continuous mapping, so t of x n converges to t of x. Okay, but what's t of xn? It's actually xn plus 1. It converges to t of x. But limit of xn is same as limit of xn plus 1, and limit of xn is x, but limit of xn plus 1 is same as limit of xn, which is equal to x. So therefore t of x is equal to x. So hence t has a fixed point. 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 Okay. So this t has a fixed. Now we prove that t has a unique fixed point. So for if it has two fixed points, so let x and y be two fixed points of t, then t of x is equal to x and t of y is equal to y. Now let us see the distance between tx and ty by applying the definition of contraction. It's less or equal to r times distance between x, y. Okay. So which means what's tx? Tx is same as x, ty is same as y. It's less or equal to r times distance between x and y. Since x and y are two distinct points, so the distance is not positive, which means that 1 is less or equal to r. A contradiction, as r is less than 1. A contradiction, as 0 less than or less than 1. So therefore t has a unique fixed point. Therefore t has a unique fixed point. T has a unique fixed point. So that proves the theorem completely. Every contraction mapping has a unique fixed point. अब इसकी एप्लीकेशन जो है वो मैं आपके लिए असाइनमेंट रख देता हूँ. एप्लीकेशन, सो प्रूव inverse function theorem. First you have to state this inverse function theorem. Okay, prove inverse function theorem by Banach contraction principle. Banach contraction principle. Okay, so that's the end of this chapter. Okay, this is